Dr. Muhammad, and this is another video under the engineering mathematics, and I'm going to talk today about the row and column spaces. Still we under the main topic of matrices, so we are going to talk today about the row and column spaces. Last video we have explained about the reduced echelon form of matrices, and today we are going to talk about something important related to this, which is the row and column spaces. Okay, now let's go and understand first and define what is the meaning of the space itself, and how we can understand it and get more regarding what we have explained last video for the reduced echelon form. So in this video we will develop three numbers associated with matrices. Actually, I'm going to talk about maybe only one thing, which is the rank. Okay, maybe we're talking about in this section, means that in the book itself. But I'm going to talk about, mainly about the ranking of the matrix. Okay. Anyway, ranking among other different types of matrices or other type of traits of the matrices is going to play a significant role in applications such as solution of system of linear equation. As we said, maybe you couldn't understand exactly what we are going to get from the concept of row and column spaces and the ranking, but you are going to realize everything when we come to the linear solution of the linear system of equation. You're going to find everything works there. The reduced form and the ranking and everything is going to work for us at this particular point. So let's now go and understand these items, and then we're going to apply them very well when we reach to the final stage of solution of linear systems or the linear system of differential equation. Okay, now let A be an n by m matrix. It is like a n rows and m columns matrix of real numbers. Each of the n rows is a vector in Rm. So we have n rows. Okay, we have n rows. So it is a vector, because if every row in the matrix, 1, 2, 3, 4, and so on. So this is considered to be a vector. Okay, vector of what? Vector of columns. The number of the span of this vector is the column. So is a vector in Rm, where m is what? It is the number of columns, as we said, number of columns. The span of these row vectors, so the span of these row vectors, the span of them, the set of all linear combination of these vectors. Linear combination. Sometimes you can find that one row is a linear multiplication of another row. Okay? This kind of relation, which is the independency or dependency between the rows, is very crucial for solution of linear equations or linear system of linear equations. So we do not like to have in one matrix or two rows that is linearly depending on one another, because at the end, when we are going to solve the set of linear equations, you are going to find that this linear or this dependency would not add anything for us. It will not help us, because they are going to be thought of as one equation, one row only. So we do not like this, and we need to put or to know from the beginning whether there is some dependency or not between the rows or between the set of equations. Okay, so now the set of all linear combination of these vectors, is a subspace of the Rm, subspace of the Rm, as we said, Rm. It is, the space is Rm, okay, and called the row space of A, the row space of A, the row space of A. This may or may not be all of Rm. So it may or may not be all of Rm, or it is less than it, depending on A. The dimension of the row space of A is the row rank. So this dimension we are going to call it row rank of A. Okay. So what is the meaning of row rank? The summary of this. Okay. The number of independent rows. That's the meaning of row rank. And similarly, we can make this 4 columns. So the m columns are vectors Rn. Okay. The span of these column vectors is the column space of A and is a subspace of Rn. Okay. And subspace of Rn. Okay. The dimension of this column space is the column rank A. So what is the meaning of column rank A? It is the columns, if we have a matrix and we have different columns, if all the columns are independent than one another, if we have 3 like this, so the ranking is 3. But if we found that 2 columns are dependent on one another, and there is, for example, only 1 column independent, then the ranking of this matrix is the column ranking is going to be 1. So the ranking means that how many independent columns that we have, if we are going to talk about column ranking, and if we are going to talk about row ranking, we are going to talk about how many rows considered to be independent, okay, in the matrix. Okay. We're going to give and explain what I have explained shortly using an example. So let's look to this example. You have A, which is 1, 2, 3, 4, 5, which is 5 rows by 3 columns. Okay, so by investigation, okay, now only by investigation now, we are going to find it a little bit difficult for you to make this, but we're going to give you a technique to understand what I have done here. If you look to this matrix, you're going to find that we have this row, which is row 1. It is a multiplication of like other rows here. So this row, for example, 5 minus 1 and 5. If you look to this row, which is 117, and this row 204, can we add them up and multiply one of them and then we can get this row? The answer is yes. Here, 5 and minus 1 and 5, it equals to minus 117, which is this third row, plus 3 times row 4, which is this. If you make this operation, you're going to find row 5 exactly. For example, minus 1 plus 3 times 2, it is 5, right? And so on. Another thing, which is this row, look to this row. By investigation, you're going to find that it equals to row 3 minus row 4. So you're going to find it like this. Row 3 minus row 4 would give you row 2. For example, this is minus 1 here, so it equals to 1 minus 2, which is minus 1. Here 1, it is 1 minus 0, it is 1. Then 3, 7 minus 4, it is 3. So this means what? This row, which is row 1, is dependent on row 3 and row 4. And also this row, which is row 2, it is dependent on row 3 and row 4. But if you look to the row 3, 4, and 5, they are independent. They are independent. Okay, that's the point. What is the meaning of independency here? That you cannot make up these rows, which is row 3, 4, and 5, from any other combinations of other rows. So they are totally independent. Okay, so we say that the rank, okay, not only rank, the row rank of A is going to be 3. Okay, what is the meaning of row rank? It is the n independent rows in the matrix. What is the meaning of dependency on independency? Already I explained them. Okay, so we call that, we can call it, instead of the rank of A, we can call it the row space, or the dimension of the row space. We call it like dimension of 3. So the dimension, sometimes they call it dimension. Okay, the dimension, okay, row space dimension, like this row space dimension. But commonly we use, I'd like to use this row rank or column rank, because we are going to find also something related to the column. Okay, in a similar fashion, if we go back here, we are going to look to the columns of this matrix. If there are some columns that is dependent on one other column or other columns, then we are going to exclude it from the number of the columns. So for example, if we found that all three columns are independent, we cannot make them up from other combinations of other columns, then the row rank of A is going to be 3. The column rank in this case would equal to 3. If we found that, for example, that we have this column is dependent on the other two columns, then, and we have two columns only independent, then the column rank in this case, it is going to be 2. Why? Because we have two independent columns. This is actually what we found here. That we found that first column, second column, third column, they are totally independent. Totally independent. So the column rank of A is 3. This means that if you try to make up one column from the other two combinations, you will not be able to do it. So this means that this column is independent, this column is independent, and this one is independent. So we found that the column rank of A is 3. There is a kind of an observation here. What was the column, the row rank? We said here, row rank, it was 3, right? Even that we have 5 rows. Here, the column rank, we found it, how much? Yes, it is 3. There is observation here? Yes, it is something. We call that this is not coincidence. Actually, the row rank equals to the column rank, always. So if we have a column rank of 3, the row rank must equal to 3. Okay? So that's an important observation. Okay? And we are going to put it as a theory here. We call it equality of row and column rank. Equality of row and column rank. Equality of row and column rank. For any matrix, the row rank equals to the column rank. For any matrix. Okay, so that's an important issue. But the point is, it is difficult to investigate, right? If we go back to the example here, how did I know that this row equals to this kind of multiplication of other rows and this one equals to this? It needs a kind of very deep investigation, right? And we cannot tell for the others. It is difficult. Yes, it is difficult. I know. So this is why we're going to get some benefits from what we have explained before regarding the reduced form of the matrix. Given an arbitrary real matrix A, it may not be obvious what the rank of A is. That's true. However, if R is the reduced matrix, then rank of R, which is going to be equal to the number of non-zero rows of R. Okay? Okay? So this non-zero rows of R, which is the reduced matrix, it is the rank of R. And this rank of R, it is the rank of A. You understand it? So this is what we are going to say. If we have A, and we make the operations, okay, on this A to get the reduced form, which is AR. Okay? This is the reduced form. If you want to know what is the rank of A, no need to make the investigation in the previous example. What you need to do is count the non-zero rows of this reduced matrix, and the number of non-zero rows is the rank of A. That easy. You understand? Okay, now let's go and have this theorem. I'm going to give an example, but I'm going to just go into the theorem first, and then I'm going to give you the example. So the theorem is, let B be formed from an n by m matrix A by a sequence of elementary row operations. Then A and B have the same row space, hence rank A equal to rank B. This is in general. If you have two matrices and you have done the same row operations on A and same row operation in B, then we are claiming that the same row space is going to be the same. Well, what is this is going to be important for us. In this sub-theory, we are going to understand it. For any real matrix A, okay, A and AR, which is the matrix itself, and the reduced form of the matrix, have the same row space. That's right. Thus, rank of A equal to the number of non-zero rows of AR. That's it. This is what I want you to remember. Okay, forget all about this kind of stuff. Just focus on this. That the rank of A, no need to investigate it by yourself as I have done in the previous examples. Just you need to have the reduced matrix and count the number of non-zero rows. This would give you the rank of A. What is the meaning of rank of A? It is the number of independent rows or independent columns, because we said that the column rank of A equal to row rank of A. They are the same. Okay? So the rank of A equals to the independent number of rows equals to the independent number of columns. Okay? So that's the important final conclusion. Rank of any matrix A equal to the rank of its reduced echelon form, which equals to the number of non-zero rows. That easy. Okay? So now I'm going to give you an example. Okay? So before going into the example, I want to show you for this example, it seems to you it was very difficult to tell, right, how we could get this kind of stuff and how we can find that this one and this one, they are dependent on others and the rank of A here equals to 3. It's difficult, right? Now it will not be difficult. What we are going to do is this A, we are going to get its reduced form, AR, as we have done in the previous video. And then you are going to count the number of non-zero rows. If you have 0 row here, then you are not going to count. So count this 1, 2, 3. Okay? Then you are going to find 3 non-zero rows. Then the ranking of A is 3. That's it. Okay, now let's have an example to understand it more. Let A equal to this matrix. Okay? So we want to know the rank of A. Actually, when you look to this matrix, it is actually a reduced form. It is 1 and everything 0 here. This is 1 leading entry, 0 here, 0 here, 1, 0 above, 0 below, and this is 0 row. So how many non-zero rows that we have? We have 1, 2, 3. So the rank of A is going to be 3. That's it. The rank of A is going to be 3. Since this is a reduced matrix, as we have seen only by observation, with 3 non-zero rows, as we say 1, 2, 3, rank A equal to 3. Rank of A equal to 3. Okay, now let's go to the next. Okay, let A be an n by n, okay, like square matrix of real numbers. Then rank A equal to n if and only if AR equal to IN. Again, if we have a matrix which is a n by n of real numbers, then the rank of this matrix is going to equal n if and only if the reduced matrix AR, we found it IN. Do you remember in the previous video I mentioned that when we reduce A to AR, we found that the reduced matrix is IN. If this is the case, then without thinking, and actually this is right, our ranking of A is going to be n. Okay, the number of rows or the number of columns. This says that the rank of a square matrix equals the number of rows exactly when the reduced form is identity matrix. Because this is right, because for the identity matrix, In, the number of non-zero rows equals to n. Okay, so this is exactly the same as we have explained in this. Okay, in this theorem. Okay, number of non-zero rows of AR. Okay, now let's have an example and see how we can apply what we have learned. Find the reduced form of the matrix and use this to determine the rank of the matrix. Also, find a basis for the row space and the matrix of the matrix and a basis for the column space. Okay, so the meaning here is we have A, which is -4 and 2, 1 and 2, 3 and 0. This is the matrix. So we need to get AR of this matrix. Then we are going to get the reduced form. It is simple routine for you. You can do it by yourself because you already have trained yourself from the previous video using the Inclass assignment and the home assignment. So you are skillful now in obtaining AR, which is the reduced form of A. We found the reduced form is going to be like this. So when you look, there is no zero rows. All of them, they are non-zeros. And how many number? What is the number of rows? Non-zero rows? 1, 2. So the rank of A is going to be 2. What is the meaning of this? That the number of rows are independent from one another because we have 2. This means that we have 2 independent rows. Exactly. Okay? So that's the rows that is going to be. The rows of A are R1 and R2, which is the first row and the second row. Okay? These are linearly independent as vectors in R3 and form a basis for the row space of A. Okay. So don't worry about the row space and this kind of stuff, and no need to go through this part, which is the row space of the matrix and so on. Okay? Do not worry about this. Just I want you to think about the rank. This is the most important part. Okay, just I want you in this section or in this area of understanding to get the rank. That's it. Forget about the basis for the row space and so on. Okay, let's go through the column. We have now 3 columns and we want to know what is the rank of the columns. Actually, without going into the details, we should say that the column rank must equal to what? Yes, equal to 2. The rank of A in terms of column, it should be equal to 2. Why? Because the row rank is 2. That's it. So we're going to find here, if you, by investigation, you're going to find that C3, which is this column, equals to -3/5 times C column 1 plus 3/5 times column 2. So this means that column 1 and 2 are independent. However, column 3 is dependent. Okay, column 1 and 2, they are independent. However, column 3, it is dependent. Okay? Okay, so now we can say that C1 and C2 are linearly independent as vectors in R. While C3, we're going to find that they have relation together. So C1 and C2 are independent and C3 it is dependent. Okay, this is by investigation. You have no way except by investigation. Okay. Okay. So now from this we need to note that the rank is equal to both the row and column rank. This is important. So if we are going to say that row rank of a matrix A equals to column rank of the matrix A. Okay? Okay? This is the important rule that you need to keep in your mind. Okay. Now let's have an example and understand. Okay? So Please forget about this, the bases and this kind of stuff. No need to go through it. Just think about the rank, okay? Okay, now we have A like this. Then you can do it by yourself. Now you can stop the video and work out the reduced form of this matrix. You're going to do it many times, so I strongly recommend to go to the previous video and know how to get the reduced form. So this is AR now. This is AR, which is 1 here, 1 here. This is right, 0 above, 0 down, and here zeros. And we have zeros, 0 rows. This means that the rank of A equals to 1, 2, which is 2. Because we have only 2 non-zero rows in the reduced matrix. Okay? Okay. Now let's go to the next, which is the another example, which is this is example. Okay, also forget about the sub bases here, just the rank is the important thing. So we have a matrix here, A. You can work out the reduced form, which is AR by yourself, and you're going to find zeros here. So we have 2 non-zero rows. So our rank, the rank of A equals to exactly 2. Okay? Okay. Now let's go to the in-class assignment, and I hope that you can get the time to get the rank. I want only the rank of these matrices. So you can stop the video here and work out the rank of these matrices. Okay, so what you're going to do, you're going to get AR for each one of them, and at the end you are going to count the number of non-zero rows. That's it. Okay, so now go and make the reduced matrix form and come back to the video. Okay, this is the solution of the in-class assignment solution. You're going to find that for A, you're going to find this is A actually, and you are going to find that the reduced form is going to be I3, which is the identity matrix. This means that the rank is 3. For problem number 2, you are going to find the reduced matrix is AR. It forms like this, 1 and 1 here, and you are going to find 2 rows only, so its ranking is 2. We have ranking 2, and we have other 2 zeros, so our ranking is 2. What is the meaning of ranking again? There are 2 rows independent, okay, and also there are 2 columns independent, okay. And for the third one, you are going to find AR equals to the identity matrix I3, then A has rank 3, okay. So this is the solution of the in-class assignment, and you are going to find it easy for you. This is the detailed solution. We have example problem 1 and 2 and 3. Here you can work, this is the detailed one. You can get AR, as you can see here. It is the identity matrix, then the rank is 3. For 2, after working all of this, do it by yourself and go through the details if you want. Then this is the IAR, and the rank is going to be 2. And this is the last one, which is the third problem. And after that, you are going to find that it's the identity matrix again. Then it is going to be the rank is going to be 3. So we have here it is 3. Here it is 2, here it is 3. This is the answer of the in-class assignment with the details. I hope that you can understand it well. Now you are prepared for the home assignment. So as I said, no need to get the basis of the row space and so on. Okay. Just what I want you to do is find the reduced form of the matrix and use this to determine the rank of the matrix. Get the rank of these matrices. Okay, this is for today's video. I hope that you understand it well and you can do the homework for this week based on the home assignment in this video. Okay, thank you and see you in the next video.